Welcome to Electronic Seed YouTube channel. Today in this video, we will learn about digital versus analog, bits, voltage levels, and resolution. Let's get started. Here's what we'll cover today, starting with the table of contents. Representing continuous analog values with discrete levels creates a trade-off between resolution and complexity. Analog signals have infinite theoretical precision, but they are very sensitive to noise. Digital systems use a limited number of levels defined by specific voltages, like 0 volts and a positive reference. If we use only 2 voltage levels, our accuracy is very coarse. This article explains how adding more switches improves resolution, links switches to binary bits, and shows real-world relevance. First, noise immunity. Digital's discrete levels can tolerate moderate interference, while analog signals degrade continuously with noise. Second, efficient bandwidth usage. Compression lets us transmit more data over the same channel. Third, encryption. Mathematical algorithms secure data, and only the correct key can decode it. Long-distance efficiency is another advantage. Repeaters regenerate digital signals without distortion, which is great for fiber, satellite, and undersea cables. But despite these strengths, a simple two-level system like 0 to 5 volts suffers from poor accuracy when representing continuous quantities. Consider a temperature sensor, where 0 to 5 volts maps linearly to -20 to +80 degrees Celsius. With a two-level system, any temperature below 30 degrees gives 0 volts, and above 30 gives 5 volts. With only 2 levels, the resolution is minimal, leading to a large quantization error. To improve accuracy, we need to increase the number of discrete levels between the minimum and maximum voltages. Think of a ruler with millimeter marks versus centimeter marks. More marks mean finer measurements. Dividing 0 to 5 volts into 16 equal steps reduces the maximum error from 2.5 volts down to approximately 0.156 volts. We can combine electronic switches using a resistor ladder or binary-weighted network. Open or off gives 0 volts, closed or on gives a weighted voltage. With one switch, we have two states, 0 volts or 5 volts. Two switches give 4 combinations. For example, off-off is 0 volts, off-on is 1.25 volts, on-off is 2.5 volts, and on-on is 3.75 volts. In general, for M switches, the number of output levels N equals 2 to the power of M. The number of switches is exactly the number of bits. 3 switches, or 3 bits, give 8 levels. 10 bits give 1024 levels. A bit is the fundamental unit of digital information, representing either a 0 or a 1. A 3-bit binary number can represent 8 distinct voltage levels. To get 256 steps between 0 and 5 volts, we solve 2 to the m equals 256, which gives m equals 8 bits. The step size is 5 volts divided by 256, which is approximately 0.0195 volts, or 19.5 millivolts of resolution. For higher precision, 16 bits gives 65,536 levels, and 24 bits gives over 16 million levels. Doubling the number of bits squares the number of levels, which dramatically improves resolution. In video, comparing 720p to 1080p, more pixels mean more spatial levels, which require more bits. File size grows from about 800 megabytes to 1.6 gigabytes. For digital audio, CD quality uses 16 bits, giving 65,536 amplitude levels. 24-bit audio gives over 16 million levels, resulting in a higher signal-to-noise ratio. Applications like autonomous driving with LiDAR, medical imaging like MRI, and scientific instrumentation commonly use 16 to 24-bit converters. Emerging fields, such as quantum computing control and high-frequency trading, require even finer voltage resolution. Adding more bits increases cost, power consumption, and design complexity. But the exponential improvement in accuracy ensures that digital systems dominate in applications where precision and noise immunity are most important.